Hey guys, it's been a long day. A little bit late, a couple hours late, but I think that's fine. Um, I'm just doing this cash, so quite frankly, I'm just recording what I normally do at night. It's just sit here and read. Uh, I just got back from the gym, so I'm all sweaty. My glasses are fogging up. All right, so let's keep reading. The Rust programming language. Chapter 7. Let's see. Managing growing projects with packages, crates, and modules. So, um, as you write large programs, organizing your code will be important because keeping track of your entire program is in your head. In your head will become impossible. By grouping related functionality and separating code with distinct features, you'll clarify where to find code and implement a particular feature and where to go to change how a feature works. The programs we've written so far have been in one module and one file. As the project grows, you can organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As the package grows, you can extract parts into separate crates and that become external dependencies. This chapter will cover all these techniques for very large projects of a set of interrelated packages that evolve together. Cargo provides workspaces, which we'll cover in Cargo's workspaces in chapter 14. In addition to grouping functionality, encapsulating implementation details lets you reuse code at a higher level. Once you've implemented an operation, other code can call that code via the code's public interface without knowing how the implementation works. The way you write code defines which parts are public for other code to use and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. A related concept in scope, the nested context in which code is written, has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can have two items with the same name in the same scope. Tools are available to resolve name conflicts. Rust has a number of features that allow you to manage your code's organization, including which details are exposed, which details are private, and what names are in each scope in your program. These features, sometimes collectively referred to as the module system, include packages, a cargo feature that lets you build, test, and share crates. Crates, a tree of modules that produces a library or executable. Modules and use let you control the organization, scope, and privacy of paths. Okay, I think we've seen use. Yeah, here. Are these modules? I don't know. We'll have to wait and see. And then paths, a way of naming an item such as a struct, function, or module. Okay. I don't know if this is like a file path or we'll have to wait and see. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have a solid understanding of the module system and be able to work with scope like a pro. And, building up to scope, they talk about why you really care about scope in Rust because, the way that they use this ownership, once it goes out of scope, everything in that method disappears. So I guess, or drops, is the term they use. So, you really do want to be really good at keeping scope, or you could be writing something and then you try to compile it and the program says, well, there's nothing there because it's out of scope or it was dropped. All right, this is short. Packages and crates. The first part of the module system will cover our packages and crates. A crate is a binary or library. The crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in the defining modules to control scope and privacy section. A package is one or more crates that provides a set of functionality. Yeah. I mean, I like the sort of theme they have going here. It's like, a barge has cargo and crates are part of the cargo. So a package is one or more crates. A package contains a cargo TOML. Yeah. So a package has one or more crates, and yeah, that describes how to build those crates. Yep. So the cargo TOML tells the package how to build the crates. Makes sense? Several rules determine what a package can contain. A package can contain at most one library crate. It can contain as many binary crates as you'd like, but it must contain at least one crate, either library or binary. Let's walk through what happens when we create a package. First, we enter the command cargo new, and then it creates a binary application. And there's the cargo.toml, the source file, and then source has the main.rs file. When you enter the command, cargo creates a cargo.toml file, gives us a package looking at the contents of the cargo.toml. There's no mention of a source stack / main rs because cargo follows a convention that knows that if the package directory contains source lib.rs, the package contains a library crate and the same name as the package, and source lib.rs is the crate root. Okay. I don't think we've done that yet. So if we enter the command, cargo creates a cargo TOML file, giving us a package. Look at the contents. There's no mention. Oh, okay. So yeah. Likewise, cargo knows that the package. Yeah. Okay. Cargo passes the crate root file to rustc to build the library or binary. Okay. Here we have a package that only contains main / main rs, meaning it only contains a binary crate named my project. If a package contains main rs and lib rs, it has two crates, a binary and a library. Both are the same as the package, both with the same name as the package. A package can have multiple binary crates in the package binaries by placing files in the source bin directory. Each file will be in a separate binary crate. So I guess I don't know what the difference is between a binary crate and a library. Maybe it'll tell me. A crate will group related functionality together in a scope so the functionality is easy to share between projects. For example, the RAN crate we use in Chapter 2 provides functionality that generates multiple numbers. We can use the functionality in our own projects by bringing the RAN crate into the project scope. All the functionality provided in the RAN crate is accessible through the crate's name RAN. Keeping a crate's functionality is its own scope. In its own scope clarifies whether particular functionality is defined in our crate or the RAND crate and prevents potential conflicts. For example, the RAND crate provides the trait named RNG. We can define a struct named RNG in our own crate because the crate's functionality is namespaced in our own crate, in our own scope. When we add rand as a dependency, the compiler isn't confused about what the name RNG refers to. In our crate, it refers to the struct RNG that we define. We would access the RNG trait from the rand crate as rand RNG. Now let's move on and talk about module systems. So, here our TOML defines, okay, so here it has the lib, and it has 2 here, and then some dependencies. Okay. I don't know if I'm very clear on crates after reading that. I'm just not sure what a crate is, why, some are binaries and some are libraries. I'm not sure about this sort of lib.rs example, but maybe since it's so short, okay, we'll explain in depth and the defining modules to control scope. Okay. But sort of, I get this part. This happens all the time in Python, and it's an issue where when you bring something into scope with like import a project, and then you can't use the keywords from, or the functions from that library in your project anymore because they're being used by the library you imported. Okay. These are short. Good. Okay. Defining modules to control scope and privacy. So in this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items, the use keyword that brings a path into scope, and the public keyword to make items public. We'll also discuss the as keyword, external packages, and Glob Operator. For now, let's focus on modules. So these are modules, or these are modules. These are crates. Pub use crate, and this is just regular use. Okay. Modules let us organize code within a crate into groups for readability and easy reuse. Modules also control the privacy of items, which is whether an item can be used by outside code, public, or is an internal implementation detail and not available for outside use, private. As an example, let's write a library crate that creates the functionality of a restaurant. We'll define the signature of functions, but leave their bodies empty to concentrate on the organization of code rather than actually implement the restaurant in code. Okay. Yeah, pseudocode is pseudocode. In the restaurant industry, some parts of the restaurant are referred to as front of the house and others as back of the house. Front of the house is where customers are. This is where the hosts seat customers, servers take orders and payments, bartenders make drinks. Back of the house is where chefs and cooks work in the kitchen, dishwashers clean up, and managers do administrative work. To structure our crate in the same way that real restaurants work, we can organize the functions into nested modules. Each create a new library named restaurant by running cargo new lib restaurant, then put the code in listing 7.1 into okay, so let's just do that. Let's see. We have a Rust tutorial Rust template, no, Rust examples, Rust projects. Okay, so here we will cargo new lib, and we'll call it restaurant. Okay, cool. And then we'll cd, well, no, let's just open it in Visual Studio, Rust projects, and then here's restaurant. Yes. And we have a source libs. Cool. Here's our package. We have, oh, it made more stuff. It wasn't done. Maybe. I don't know. It took a minute. Okay. And then, you just have this sort of code here. Just copy this and put it in our libs. There's our test. We can just leave the test where, yeah, and we save this, and it's like, hey, this doesn't, you never use this. Okay, good Rust. Okay, we define a module by stating that by starting with the mod keyword and then specify the name of the module, in this case front of house. Okay, and then we place curly brackets around the body of the module. Inside modules we can have other modules, as in this case the modules hosting and serving. Modules can also be definitions for other items such as structs, enums, constants, traits, or as in 7.1 functions. Yep. So we have a mod called front of house with two mods, one for hosting and one for serving. By using modules, we can group related definitions together and name why they're related. Programmers use this code. Using this code would have an easier time finding the definitions they wanted to use because they could navigate the code based on the groups rather than having to read through all the definitions. Yeah, programmers adding new functionality to this code would know where to place the code to keep the program organized. Earlier, we mentioned that source main RS and source lib RS are called crate roots. The reason for their name is that the contents of either of these two files from a module named crate at the root of the crates module structure known as the module tree. Okay. Yeah. Okay. Yeah, because they're the root of the crate. Okay. That's like the longest sentence to say that this is called the root because they're at the root of the crate, and we call this a module tree. Okay, I don't know. It's easier to explain in person than in text, I guess. This tree shows how some of the modules nest inside one another. For example, hosting nests inside front of house. The tree also shows that some modules are siblings to each other, meaning that they're defined in the same module. Yep. To continue the family metaphor, if module A is contained inside module B, we say that A is a child of module B and B is a parent of module A. Notice that the entire module tree is rooted under the implicit module named crate. The module tree might remind you of a file system directory tree on your computer, and that is, this is a very apt comparison. Just as directories in a file system, your modules, you use modules to organize your code, just like files in a directory. Which I don't do very well, you know. But, you know, file management is on your personal machine is different. It's a different topic. We could go into that. I saw another guy on, speaking of operating systems, I saw another guy on Twitch and the software programming. They spent their whole stream like setting up an Ubuntu virtual machine. So, or it wasn't Ubuntu, it was KDE, but I feel like maybe I should try that. Maybe it'll get some people to view. Anyways, I'm going to finish this chapter up. Yeah, they're short. It's short stuff. Oh, excuse me. Yeah, short stuff. So I'll just read this chapter and then we'll move on from. Well, I'll close out the stream since I started so late. Paths for referring to an item in a module tree. To show Rust where to find an item in a module tree, we used a path in the same way we use a path when navigating a file system. I knew it. If we want to call a function, we need to know its path. The path can take two forms: the absolute path from a crate root by using a crate name, or a literal crate, a relative path starting from the current module and use self, super, or an identifier in current module. Both absolute and relative paths are followed by one or more identifiers separated by double colon. Let's return to the example. How do we call the add to waitlist function? This is the same as asking what's the path of the add to waitlist function. I don't know if that's the same as asking. I think you just get the same answer when you ask those questions. So that does, I don't know. That's semantics though. We simplify our code a bit by removing some of the modules and functions. We'll show two ways to call the add to waitlist function and new function eat at restaurant. Okay, defined in the crate root. Yeah, okay. The eat at restaurant function is part of our library's crate's public API. So we make it with the pub keyword. Okay, yeah. In the exposing paths with the pub keyword section, we'll go into more detail. Okay, about pub, note that this example won't compile just yet. We'll explain why in a bit. So he has this mod, and he has his hosting mod in that mod, and he has a function in that hosting mod called add to waitlist. And then he has a public function called eat at restaurant that he writes an absolute path. So it's in a crate. It's in crate, then front of house mod, then hosting, then add to waitlist. Or you could use the relative path, which is just front of house, hosting, add to waitlist, which you don't need this crate because this function is in the same crate as this mod, right? I assume so. The first time we call add to waitlist function in eat at restaurant, we use an absolute path. The add to waitlist function is defined in the same crate as eat at restaurant, which means we can use the crate keyword to start the absolute path. The add to waitlist function is defined in the same crate. Yeah, so that's what I thought. Okay, sorry, I got pinged by. Let's see. We call the add to waitlist function eat at restaurant function. Okay, I'm reading the same thing because I just got a message. Sorry, guys. Let's switch back to my Twitch stream. Okay. After crate, we include each of the successive modules until we make our way to add to waitlist. You can imagine a file system with the same structure. We'd specify the path, yeah. And to run add to waitlist program using the crate, start from the crate root is like / to start from the file system root in your shell. The second call, add to waitlist, we use a relative path. The path starts with front of house, the name of the module defined at the same level of the module tree as eat at restaurant. Here, the file system equivalent would be using the path. Starting with the name means the path is relative. Yes. Relative to the location that you are in. So it's like when you start up your command line and you just happen to be in the same folder that front of house is at. Choosing whether to use a relative or absolute path is a decision you'll make based on your project. The decision should depend on whether you're more likely to move item definition code separately from or together with the code than that uses the item. For example, if we move front of house module and the eat at restaurant function into a module named customer experience, we'd need to update the absolute path to add to waitlist, but the relative path would still be valid. Okay. However, if we move eat at restaurant function separately into a module named dining, and the absolute path dining, the absolute path of the add to waitlist call would stay the same, but the relative path would need to be updated. Our preference is to specify absolute path because it's more likely to move code definitions and item calls independently of each other. Sure. Let's try to compile listing 7.3 and find out why it won't compile yet. The error we get is shown in listing 7.4. So cargo build, okay. So the module hosting is private. Okay. Okay. And then mod hosting. Oh, okay. So it's because eat at restaurant is public and it's accessing a private, because I guess mods are private by default. For security, probably, because it's Rust. The error message says that module hosting is private. In other words, we have the correct path for hosting module and add to waitlist function, but Rust won't let us use them because it doesn't have access to the private sections. Modules aren't useful only for organizing your code. They're also define Rust privacy boundary, the line that encapsulates the implementation details external code isn't allowed to know about, call, or rely on. So if you want to make an item like a function or struct private, you put it in a mod. The way privacy works in Rust is that all items, function, methods, structs, enums, modules, and constants are private by default. I guessed it. Items in a parent module can't use the private item inside child module, but items in the child module can use the items in their ancestor modules. Okay, yeah. The reason is that the module, it's weird they say ancestor module. I think most people just say parent module, right? But I guess it can go down modules for days. The reason is that child modules wrap and hide their implementation details, but the child modules can see the context in which they're defined. To continue with the restaurant metaphor, think of the privacy role as being like the back office of the restaurant. What goes on in there is private to restaurant customers, but office managers can see and do everything in the restaurant in which they operate. Rust chooses to have the module system function this way so that hiding inner implementation details is the default. That way, you know which parts of your inner code you can change without breaking outer code. But you can expose inner parts of child module code to outer ancestor modules by using the pub keyword and make them public. So let's return to the error in 7.4 that told us that the hosting module is private. We want the eat@restaurant function in the parent module to have access to the add to waitlist function in the child module. So we mark the hosting module in the pub with the pub keyword here. Okay. Unfortunately, the code still results in errors. Okay, so add to waitlist is private. Wow. Do you have to add pub to that too? What happened? Adding a pub keyword to the host with this change, if we access front of house, we can access hosting, but the content of hosting is still private. Making the module public doesn't make the contents public. The pub keyword on a module only lets code and its ancestors refer to it. Oh, so front of house can refer to the hosting. So, okay, the errors on this example say that add to waitlist function is private. The privacy rules apply to everything. Well, structs, enums, functions, and methods, and modules. Methods and modules. That's a lot of stuff, I guess, but variables aren't on that list, so I don't know. Yeah. Let's also make the add to waitlist function public by adding the pub keyword before its definition. Okay. Yep. Now the code will compile. Let's look at the absolute and relative paths and double check why adding pub keyword lets us use these paths in the add to waitlist with respect to the privacy rule. In the absolute path, we start with crate, the root of the crate module tree. Yes. Then the front of house module is defined in the crate root. The front of house module isn't public, but because the eat@restaurant function is defined in the same module as front of house, that is, eat@restaurant and front of house are siblings, we can refer to front of house from eat@restaurant. Next is the hosting module marked with pub. We can access the parent module of hosting, so we can access hosting. Finally, the add to waitlist function is marked with pub, and we can access the parent module, so this function call works. In the relative path, the logic is the same as the absolute path, except the first step, rather than starting from the root, the path. I mean, this seems obvious. No need to say all of that. I don't think you need to explain that. Since this can access this, you can access this because it's public, and you can access this because it's public. Yeah, I don't know. Seems pretty straightforward. Starting relative paths with super. We can also construct relative paths with that begin in the parent module by using super at the start of the path. That is starting a file system path with ... syntax. Why would you want to do this? Consider the code in 7.8 that models the situation in which a chef fixes an incorrect order and personally brings it out to the customer. The function fix incorrect order calls the function serve order by specifying the path to serve order starting with super. Okay. So this is a function. Okay. You can also construct relative paths that begin. Right. You don't have to say crate. You can say super. You just go up one out of the mod to this function. Yeah, the fix incorrect. Okay, it means like ... in the, which I use all the time, cd ... But anyways, it means go up one directory. The fix incorrect order function is in the back of house module. So we can use super to go to the parent module of the back of house, which is this case a crate, the root. From there we look for serve order and find it success. We think back of house module and the serve order function are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crates module tree. Therefore, we use super, so we'll have fewer places to update code in the future if the code gets moved to a different module. Okay. Making structs and enums public. We can also use pub to designate structs and enums as public, but there are a few extra details. If we use pub before a struct definition, we make the struct public, but the struct's fields will still be private. That's crazy. We can make each field public or not on a case-by-case basis. In listing 7.9, we've defined a public back of house breakfast, okay, struct with a public toast, okay, field by a private seasonal fruit field. This model is the case in a restaurant where a customer can pick the type of bread that comes with a meal, but the chef decides which fruit accompanies the meal based on what's in season and in stock. The available fruit changes quickly, so customers can't choose the fruit or even see which fruit they'll get. Okay. Yeah. Okay. Yeah, so that's a struct. And then, is that an enum? Where's the enum? This is just a struct with two strings, right? Oh, okay, we're not talking about, this is just a struct, yeah. Okay, they just mentioned enums, but they didn't use an example with an enum. Gotcha. Okay, because the toast field in the back of house breakfast struct is public and eat at restaurant, we can write and read to toast field using dot notation. Notice that we can't use the seasonal fruit field in the eat at restaurant because seasonal fruit is private. Try uncommenting the line, modifying the seasonal fruit field. Okay, yeah. uh, field value to see what error you'll get. I mean, I would guess that you would have the seasonal fruit is private error. Also note that because back of house breakfast has a private field, the struct needs to provide a public associative function that constructs an instance of breakfast. We've named it summer here. Okay. Also note that because back of house breakfast has a private field, yeah, the struct needs to provide a public associated function that constructs an instance of breakfast, yeah. If breakfast didn't have such a function, we could create an instance of breakfast and eat at restaurant because we couldn't. Oh, I see. We can only yeah, we can only. Oh, that's so weird. If breakfast didn't have such a function, we could create an instance of breakfast at Eden Restaurant because we couldn't set the value of private seasonal field in Eat at Restaurant. That's interesting. So since these are, so you can make a breakfast called summer, and you can add toast and peaches here. You can't do that here because peaches is private and this is public. You can do it here because they're in the same mod, which is private. But since toast is public, you can change it here. But since fruit isn't private, you can't change it here. I mean, I guess that doesn't sound very complicated, but it just feels weird, I guess. That you would, I mean, it makes sense that if you wanted to change it here, or even to make it here, you would have to make this public. But you can't change this at all. It is what it is. It is what it is. Okay, so here, in contrast, if we make an enum public, all of its variants are then public. We only need the pub before enum keyword. Because we've made appetizer enum public, we can use soup and salad variants and eat at restaurant. Enums aren't very useful unless the variants are public. It would be annoying to have to annotate all enum variants with pub in every case. So the default for enum variants is to be public. Structs are often used without the fields being public. So struct fields follow the general rule of everything being private by default unless annotated with pub. There's one situation involving pub that we haven't covered, and that's in our last module system feature, the use keyword. We'll cover use by itself first, and then we'll show how to combine pub and use. Okay. Bringing paths into scope with the use keyword. So it might seem like paths we've written to call functions so far are inconveniently long and repetitive. For example, in 7.7, whether we choose the absolute or relative path of add to waitlist function every time we want to call add to waitlist, we have to specify front of house and hosting 2. Fortunately, there's a way to simplify this process. We can bring a path in scope once and then call the items in a path as if they're local items with the use keyword, like we've been doing. We bring the crate from front of house hosting module into scope of the eat at restaurant function. So we only have to specify hosting add to waitlist to call the add to waitlist function in eat at restaurant. So you use create front of house hosting, and now you can just use it now you just use it hosting add to waitlist. Adding use and a path in the scope is similar to creating a symbolic link in the file system by adding use create front of house hosting in the create root. Hosting is now a valid name in the scope, just as though the hosting module had been defined in the create root. Paths brought into scope with use also check privacy as other paths. You can also bring an item into scope with use and a relative path. Shown 712 shows how to specify a relative path to get the same behavior in 711. Use self front of house hosting. So not that much shorter, but I mean, I guess if you have mods on mods on mods, maybe it's easier to just call self instead of create. Or if, yeah, okay. I'm not really sure. I mean, if it's the same length, I don't know. In 711, you might have wondered why we specified use create front house hosting and called hosting add to waitlists and eat at restaurant rather than specifying use path all the way to add to waitlist function to achieve the same result as in 713. Although both listings 711 713 accomplish the same task, using 711 and is the idiomatic way to bring a function in scope with use. Bringing the function's parent module into scope with use means we have to specify the parent module when calling the function. Specifying the parent module when calling the function makes it clear that the function isn't locally defined while still minimizing repetition of the full path. The code is in listing 7.3 is unclear as to whether add to waitlist is defined. On the other hand, when bringing a struct enum and other items with use, it's idiomatic to specify the full path. 714 shows the idiomatic way to bring a standard library's hash map struct into the scope of a binary create. Hash map new. So here, you just want to use hash map. You bring the whole thing in because it's a struct. There's no reason behind the idioms. It's just the conventions that have emerged, and folks have gotten used to reading and writing Rust code this way. The exception to this idiom is if we're bringing two items with the same name into scope with use, because Rust doesn't allow that. Listing 715 shows how to bring two result types into scope that have different that have same name but different parent modules and how to refer to them. Yeah, that makes a lot of sense. As you can see, using the parent modules distinguish the two result types. If instead we specified use standard format result and use standard IO result, we'd have two result types in the same scope, and Rust wouldn't know which one we meant when we used result. Yeah. There's another solution to the problem of bringing two types of the same name into the same scope with use. After the path, we can specify as and a new local name or alias for the type. Another way to write code is in listing 715 by renaming one of the two results as IO result. Okay, and in the second use statement, we choose the name IO result for the standard IO result type, which won't conflict with the results from standard format that we've also brought into scope. Listing 715 and listing 716 are considered idiomatic, so choice is up to you. This is like Python, so, but I'm not particularly fond of this. I think that you know, a lot of standards come up with this. People just make up like as whatever, and I don't know, how you define what this as is going to be like. IO result, is this standard? Is this what people have been calling this IO result library? I don't know. The naming conventions, like if I named it poop, people start calling IO result poop. I don't know. Maybe. Probably not, because that's stupid. But anyways. Re-exporting names with pub use. When we bring a name into scope with the use keyword, the name available in the scope is private. To enable the code that calls our code to refer to that name as if it had been defined in the code scope, we can combine pub with use. This technique is called re-exporting because we're bringing in an item into scope that we make, but also making that item available for others to bring into their scope. 717 shows the code in listing 711 with use in the root module changed to pub use. Okay. By using pub use, external code can now call the add to waitlist function using hosting add to waitlist. If we hadn't specified pub use, the eat at restaurant function could call hosting add to waitlist in its scope, but external code couldn't take advantage of this new path. Interesting. Re-exporting is useful when the internal structure of your code is different from how programmers calling your code would think about the domain. For example, in this restaurant metaphor, the people running the restaurant think about front of house and back of house, but customers visiting the restaurant probably won't think about the parts of the restaurant in those terms. With pub use, you can write our code with one structure but expose a different structure. Doing so makes our library well organized for programmers working on the library and programmers calling the library. I don't know. In chapter 2, we programmed a guessing game project that used an external package called ran to get random numbers and used ran in our project. We added this line to the cargo toml. Adding ran as a dependency in cargo toml tells cargo to download the ran package and any dependencies from crates.io and makes ran available in our project. Then to bring ran definitions into scope of our package, we used a use line starting with the name of the crate ran and listed the items we wanted to bring into scope. Recall chapter 2, we brought the RNG traits into scope and called the ran thread RNG function. Yep, I remember that. Members of the Rust community have made many packages since available in Crate.io, and pulling any of them into your package involves the same steps: listing your packages in cargo toml file and using use to bring them into scope. Note that the standard library is also Crate that's external to our package. Because the standard library is shipped with the Rust language, we don't need to change cargo toml to include std, but we do need to refer to it with use to bring the items from there into our package's scope. For example, with hash map, we would use this line. It's the absolute path starting with std, the name of the standard library Crate. Using nested paths to clean up large use lists. If we're using multiple items defined in the same crate or same module, listing each item on its own line can take up a lot of vertical space in our file. For example, with 2 use statements we had in the guessing game, bring items from std into scope. Yeah. Instead, we can use a nested path, bring the same items into scope in one line. To do this, we specify the common part of the path and then followed by 2 colons and then curly bracket around the list of the paths that differ. Okay. In bigger programs, bringing many items into scope from the same crate or module using nesting paths can reduce the number of separate use statements needed by a lot. We can use the nested path at any level in a path, which is useful when combining 2 use statements that share a subpath. For example, 7.9 use statement IO write into scope. The common path for these is stdio, and that's the complete first path. To merge these 2, you can use self in the nested path. Okay, yeah, because it's self refers to stdio. Yeah, and then write just appends itself to stdio. Yep, as shown here. Glob Operator. If we want to bring all public items defined into a path, in a path into a scope, we can specify the path followed by the Glob Operator. This use statement brings all public items defined in std collections in the current scope. Be careful when using the Glob Operator. Glob can make it harder to tell what names are in scope and where a name used in your project, in your programs are defined. The Glob Operator is often used when testing to bring everything under test into the test module. We'll talk about how to write tests section in chapter 11. The Glob Operator is also sometimes used as part of the prelude pattern. See standard library documentations for more information on that pattern. All right, let's chapter. Separate modules into different files. So far, all the examples in this chapter define multiple modules in one file. When modules get large, you might want to move their definitions to a separate file to make the code easier to navigate. For example, let's start with code at listing 717, move the front of house module to its own file, source front of house rs. By changing the crate root so it contains the code shown in listing 721. In this case, the crate root file is source librs, but this procedure also works with binary crates whose crate root file is source main rs. So mod pub use crate front of house hosting, eat at restaurant hosting, add to waitlist. So that's what it looks like. The source front of house gets the definition from the body of the front of house module as shown in 7.2. 722. Okay. Using a semicolon after mod front of house rather than using a block tells Rust to load the contents of the module from another file with the same name as the module. To continue with our example, and extracting host module to its own file as well, we'll change source front of house rs to contain only the declaration of the hosting module. When we create source front of house directory and file source front of house hosting rs to contain the definition made in hosting module. Okay, So we just put the function in the file here. And this is a folder now. The module tree remains the same. The function call in eat at restaurant will work without any modifications, even though the definition lives in a different file. This technique lets you move the modules to new files as they grow in size. Note that pub use create front of house hosting statement and source librs also hasn't changed, nor does use have any impact on what files are compiled as part of the crate. The mod keyword declares modules, and Rust looks in a file with the same name as the module for the code that goes into that module. I wish they'd showed you the file directory that of this. You know, they show you the file name, but they don't show you the structure of the files. Yeah, so it's weird that is it's weird that you have the front of house rs and the front of house directory. Let me see. Let me open just this near NFT tutorial. So so it's a librs, right? And here we have these. So here's the librs, right? And we got metadata here. Create. So everything that's in the root, and we're importing metadata, mint, just everything, and it's public. Approval. Yeah. Yeah. And where do they call these? I guess I have to use them. I have to use those crates in here. Okay. Yeah. Okay. It makes sense. Let's look at the json.tom or the cargo.tom. And here we only have one dependency. Okay. Okay. So summary. Rust lets you split a package into multiple crates and a crate into modules so you can refer to items to find one module from another. You can do this by specifying absolute or relative paths. These paths can be brought into scope with a use statement, so you can use shorter paths for yada yada yada. All right. I can't wait for 10. I think that's where it gets crazy, right? Maybe this never gets crazy. I don't know. Maybe I should just learn how to program with Rust. Maybe I should just write a program. I don't know. But I feel like I know more about Rust the more I read about it. So, I mean, and we're almost halfway done with this book. So, yeah, we'll keep going until we're finished. Anyways, see you guys later.